Okay, let's look at this problem. We have a mixing chamber. Okay, let me write down the energy balance equation. So we have two inlets, inlet number 1, number 2, and one exit, number 3. So if we have two inlets and one exit, the energy balance equation is Q in plus W dot in plus M dot from the inlet number 1. This one has enthalpy, kinetic energy, and potential energy. We have another inlet number 2. So we have M dot number 2. This one has specific enthalpy, kinetic energy, and potential energy. And the energy transfer out of this mixing chamber, we have heat transfer, energy transfer by work, and the exit number 3, M dot number 3. This one has enthalpy, kinetic energy, and potential energy. First of all, we can neglect the kinetic energy change and the potential energy change, assuming that this one has a good insulation. So we can neglect heat transfer, and there is no information about energy change, energy transfer by work, so we can neglect W in and out. Then we have these three terms in this equation. They are M dot number 1 H1 plus M dot number 2 H2 is going to be M dot number 3 H3. We can also consider the mass balance equation. We have two inlets and one exit. The sum of the mass flow rates at number 1 and number 2 should be the same as the mass flow rate at number 3. So these are the governing equations in this problem. So now let's see what do we know in these equations. First, we have the temperature and pressure at the inlet number 1, so we can determine H1. We have the temperature and pressure at the inlet number 2, so we can determine H2. We have the temperature and pressure at the exit, so we can determine H3. We also know the mass flow rate at number 1, which is 0.5 kilograms per second. So we know M dot number 1 here. So the only unknowns are M dot number 2 and M dot number 3. So we have two unknowns and two equations. So we can determine the mass flow rate at the inlet number 2, M dot number 2 here, this one. So let's find H1, H2, H3. Since we have water which can undergo phase change, we need to determine the phase change process of this water. So to do so, we need to make a property diagram. Since we have the same pressure, 250 kilopascal, so let's use this pressure to determine the phase. So if at this pressure, 250 kilopascal, we can make temperature diagram. The temperature diagram is going to be T, V, T, U, T, H. Anything is fine. However, in this energy balance equation, we have H. So why don't we make TH diagram? TH diagram looks like this. To complete this TH diagram, we need to know three properties, they are he set the saturation temperature at 250 kilopascal. In other words, at what temperature this water boils at this pressure, and HF, the specific enthalpy of saturated liquid, Hg, the specific enthalpy of saturated vapor. We can find T set HF, Hg from where? From this pressure. That means we need to go to find the saturated water pressure table, which is right here, table A3. Properties of saturated water pressure table. So if you know pressure, you can find their properties. In this case, if you look at the first column, we have pressure, which is 2.5 bar. 1 bar is 100 kilopascal. So this is 250 kilopascal. So any numbers on this line can be used to complete this TH diagram, since we know T set, the saturation temperature, which is here, 127.4. And HF, 535.37, Hg, 2716. So that's how we can make this TH diagram. Then, what is the temperature at each inlet and the exit? The highest temperature is going to be 80 degrees Celsius. So where is 80 degrees Celsius? Lower than this temperature. So 80 degrees Celsius, something, around here. So the only possible phase change process is going to be number 1, compressed liquid. What about 20 degrees Celsius? Here, T number 1, 42, somewhere here. So still number 1. So it is phase change process number 1, compressed liquid. If you have compressed liquid, by the way, we all know this is number 1, this point is number 2, here is number 3, this one is number 4, and here we have number 5. So we have 5 phase change processes. According to the temperatures we have on this TH diagram, the only phase change process possible is going to be number 1, compressed liquid. If you have compressed liquid, there are 2 ways to evaluate its properties. The first one is when pressure is high, usually equal to 2.5 megapascal or greater than 2.5 megapascal. If it is water, we can go to table A5. But if the pressure is less than this value, then we assume that the properties of this compressed liquid can be approximated as the properties of saturated liquid at the same temperature. So the important thing is that at the same temperature, not the pressure. So if we want to determine specific enthalpy H, this specific enthalpy H is going to be HF at the same temperature. So at H number 1 is going to be the one of compressed liquid, compressed liquid, compressed liquid. So how can we evaluate H1, H2, H3? They are HF at the given temperature. So H1 first, what is the temperature at this point? It is going to be HF at 80 degrees Celsius. What about H2? What is the temperature at the inlet number 2? 20 degrees Celsius. HF at 20. What about H3? HF at 42 degrees Celsius. So you just need to find these 3 values, then you can to solve these equations. So let's find HF. Here is table A2. We have saturated water. Since we are going to find these HF values at these temperatures, since we're using temperatures, we need to go to the temperature table. So where is 80 degrees Celsius? Right here. So what we are looking for, HF. HF is here. So the number we are looking for is going to be 334.91. 334.91. What about 20 degrees Celsius? At 20 degrees Celsius, HF is 83.96. 83.96. What about 42 degrees Celsius? We don't have 42 degrees Celsius. It's going to be between 40 and 45. So you need to do a linear interpolation to determine HF at 42 degrees Celsius. You already know how to do a linear interpolation, right? Let me do one last time, okay? One last time. This is the last time I'm going to do linear interpolation ever in this class. So the left-hand side is what? Temperature T. The right-hand side is HF. So what do we have? Between 40 and 45. So I'm going to write it is between 40 and 45. What are the HF values at 40 and 45? They are 167, 188. So I'm going to write these numbers in the same location on the right-hand side. At 40, which is bottom left, here on the right-hand side, bottom left, we have 167.57. At 45, 188.45. Then what is the temperature? At what temperature we want to evaluate its HF? 42. So I'm going to write 42. That is the top left on the left-hand side. So top left of the right-hand side is the unknown HF. Then we can finish this equation by writing 45, 188.45. That's how you can determine HF at 42 degrees Celsius. So if you do, you get 175.92. So we have H1, H2, H3. We have m dot number 1, which is 0.5 kilogram per second. We only have have two unknowns, m dot number 2 and m dot number 3. So you can determine m dot number 2. That's what we want to determine, which is 0.864 kilogram per second. So that's how you determine, and that's how you solve this problem. So we have two equations and two unknowns, right? So then you can find this one. Look at this one. This one is m dot number 3 is 0.5 kilogram per second plus m dot number 2. So instead of this, you can say this one is 0.5 kilogram per second plus m dot number 2. Then how many unknowns do you have? Just one, m dot number 2. Then you have this equation. You can find m dot number 2. Any question? Is it too fast? Too slow? A little fast. Okay. Mhm. Not difficult, right? It's Thermo 1. You are here for Thermo 2. So if you are disappointed with the difficulty of this question, then don't worry about that. Next week, we can study Thermo 2. Okay, I have one more problem, which is heat exchanger. Heat exchanger. By the way, there are many thermodynamic devices that we studied in chapter 4 in EGR456, but we only study mixing chambers and heat exchangers because these are the ones that we study in Thermo 2. Okay, when we have moist air, a mixture of dry air and water vapor, that is our system. And when we have a chemical reaction. So those are the two things that we are going to use: mixing chambers and heat exchangers. So everything is the same. We are going to study the energy balance equation and those first law of thermodynamics and second law of thermodynamics. However, we are not going to use a simple water or the gas like carbon dioxide, oxygen, etc. We are going to use moist air. So it is going to be a mixture of dry air and water vapor, the real air here. So that's what we are going to study using the same, the open systems and the closed systems analysis that we already did. We are going to just change our system, moist air. That is going to be the first chapter. The second chapter is going to be when we have chemical reaction. That's the second chapter. So we are going to study only 2 chapters in Thermo 2. So this one is heat exchanger. So let's see how we can solve this problem. Studying heat exchanger is not very difficult. So heat exchanger means that you have 2 different fluids exchanging heat, but they do not mix. So that is the definition of heat exchanger. So they look like this. So we have one fluid goes in, maybe hot fluid or cold fluid, I don't know, and it comes out. So there is an inlet and the exit. And there's another fluid going in this direction and leaves at this exit. So what happens is that if one is at higher temperature than the other, there is a heat transfer from high temperature fluid to a low temperature fluid. However, you can see they do not mix. That is heat exchanger. Where we use heat exchanger? Many places. What about this air conditioning system? What is the working fluid of this air conditioning system? Air? Yeah, that can be one. There is a refrigerant. So 2 of them. There are 2 fluids in this air conditioning system. But do you want to breathe refrigerant? No. So on the air, that comes into the classroom and then goes, goes back to the air conditioning unit where there is a heat transfer between air and refrigerant. They don't mix, so we don't breathe refrigerant, right? Then how can we, write the energy balance equation? It's simple. If we have, let's say that there is one fluid that goes in at the inlet number 1, and then leaves this heat exchanger at the exit number 2, and there is another fluid, that goes into this heat exchanger at inlet number 3, and this one leaves at the exit number 4. Then we can make 3 energy balance equations. one for this fluid, another one for this fluid, and the last one for the entire heat exchanger. Okay, so let's do one by one. If I say, the fluid that goes in at the inlet number 1 is fluid A, and there's a fluid B goes into this heat exchanger at the inlet number 3. So there are two fluids, A and B. Then you can make an energy balance equation for A, another energy balance equation for B, and one energy balance equation for both of them. Okay? And let's assume that fluid B is at higher temperature than fluid A. Then what is the heat transfer direction? From fluid B to A. So there is heat transfer Q. By the way, this is an open system, right? So when we have an open system, it is convenient to use rate form, which means energy per time. So instead of Q, I'm going to say Q dot. What is the difference between Q and Q dot? Q is the amount of heat transfer. Q dot is the rate of heat transfer. Okay? So Q divided by time. So this is the assumption. Let's write down the energy balance equation for A first. So the energy balance equation, the general energy balance equation looks like this. Let me write the general energy balance equation first. Q dot in plus W dot in, and we have the one inlet. Let's assume that we have one inlet. Then M dot, this one, at its inlet, it has enthalpy, kinetic energy, and potential energy, gravity times elevation Z. So these are energy transfer into a system. And we have energy transfer out of a system, Q dot out plus W dot out plus M dot at its exit. It has enthalpy, kinetic energy, and potential energy. So this is the general energy balance equation. And we can neglect kinetic energy change and potential energy change. In a heat exchanger, we usually do not expect any energy transfer by work. So you can neglect these two. So what we have? We have the enthalpy transfer at the inlet and its exit and possible heat transfer. Not both, one of them, depending on the direction of the heat transfer. So based on that, let's write the energy balance equation for A per unit time. So what is the inlet? And what kind of heat transfer? There is an incoming heat transfer, right? Because the fluid B is at higher temperature, so incoming heat transfer. What is incoming heat transfer? This one. Then we don't have this one, right? So for fluid A, the energy balance equation is we have an incoming heat transfer for the amount of Q dot. So we have Q dot plus the enthalpy transfer rate at the inlet, which is number 1. M dot number 1, H1. What else? We have enthalpy transfer rate at the exit, which is number 2. M dot number 2, H2. Since there is only one inlet, one exit, so we can combine M dot number 1 and M dot number 2. So it's going to be just M dot of A. So we can say M dot of fluid A. So we can rewrite this equation as Q dot, if we move this one to the right hand side, Q dot is m dot of fluid A times H2 minus H1. So this is one energy balance equation for fluid A. What about fluid B? For B, do we have Q in? No, this one is outgoing heat transfer rate, so which is this one. So let's consider the enthalpy transfer rate at the inlet. The inlet is number 3. So m dot number 3 times H3, then we have Q dot out. For the amount of Q dot is Q dot plus the enthalpy transfer rate at the exit, and its exit is number 4. So m dot number 4, H4. So this is the energy balance equation. So let's simplify this one. We can move this one left-hand side, and m dot number 3 is the same as m dot number 4 because we only have one inlet, one exit for fluid B. So we can just say m dot of B. So if we say m dot of B, m dot of B, then what is the energy balance equation? M dot B times H3 minus H4 is Q dot, what is this number 3? Q dot. So this is the energy balance equation for fluid B. Then the third one is we can write down the energy balance equation for the entire heat exchanger. So the control volume is going to be this much. So how many inlets and how many exits for this heat exchanger? 2 inlets, number 1, number 3, 2 exits, number 2 and number 4, right? Then, if we write the energy balance equation for the entire heat exchanger, what is the heat transfer? Can we say this Q dot? Not anymore. If you consider the entire heat exchanger, this Q dot is what happens inside the system, so that's not our interest. When we talk about energy transfer, either Q or W, we only consider the energy transfers between the system and its surroundings. So the Q dot inside the heat exchanger is not gonna, there's no place for this Q dot in this energy balance equation. So there's no Q dot in, Q dot out, only enthalpy transfer rate at the inlet. So how many inlets? 1 and 3. So we can say m dot number 1, H1, then we have another inlet, number 3, plus m dot number 3, H3. So we have 2 inlets and 2 exits. M dot 1 exit, number 2. Number 2, H2, plus m dot number 4, H4. Then let's simplify this equation. By how? M dot number 1 is the same as m dot A. M dot number 2 is also the same as m dot A. So we can say this one is m dot A. This one is m dot A. What about m dot number 3 is the same as m dot B? M dot number 4 is also m dot B. So we can say this one is m dot B, m dot B. So why don't we move this one to the left-hand side, this one to the right-hand side? Then the energy balance equation becomes m dot B H3 minus H4 is going to be m dot A H2 minus H1. So these are the 3 energy balance equations, 1, 2, 3 for heat exchanger. So why don't we use MB instead of M3 or M4? Because, if we use this equation, how many unknowns? 1, 2, 3, 4, 5, 6, 7, 8. If you use this equation, how many unknowns? 1, 2, 3, 4, 5, 6. You can eliminate 2 unknowns. Okay, and let's solve a problem together. So we have a heat exchanger. That's one. Steam enters the condenser of a steam power plant at 20 kilopascal and a quality of 95% with a mass flow rate of 20,000 kilogram per hour. It is to be cooled by water from a nearby river. So what happens? The fishes in the river is going to die, right? No. By circulating the water through the tubes within the condenser. So to prevent thermal pollution, the river water is not allowed to experience a temperature rise above 10 degrees Celsius. Temperature rise by 10 degrees Celsius. It's already too much, isn't it? Imagine that the outside temperature goes by 10 degrees Celsius. It's going to be 18 degrees Celsius, 18 degree Fahrenheit increase. So Michigan becomes like Texas, right? No? Okay. So if the steam is to leave the condenser as a saturated liquid at 20 kilopascal, determine the mass flow rate of the cooling water required. One thing we can notice is that the pressure at the inlet of the steam is pretty low. Why is that? We studied in chapter 8, EGR456. If you decrease the condenser pressure, you can increase the enclosed area of the Rankine cycle to increase the efficiency. You remember? You can go check EGR456, chapter 8. So the lower, the condenser pressure, higher thermal efficiency you can achieve because you can produce more work. Anyway, let's solve this problem. We can reuse, I think we can reuse this this heat exchanger. It looks too complicated. Just a little. Okay. So let's rewrite this heat exchanger. So we have this one as small as possible because I need to write a lot here. So there's number 1, inlet. Number 2, the exit. Number 3, inlet for the steam. Number 4 is the exit for the steam. Okay, so we have a steam which is going to be at high temperature. So steam here. And enters at number 3, leaves at number 4. And we have river water here, enters the heat exchanger at number 1, leaves at number 2. Okay, so what happens? So there's a heat transfer from the steam to the river water for the amount of Q dot. Okay, let me reuse the energy balance equation here. Okay, since you already know how we got these energy balance equations, so let me rewrite this one somewhere here. The first one is Q dot is M dot A. What is A, by the way? Oh, A is the river water. River water is A. Steam is B. So M dot A times H2 minus H1. The other one is M dot B. H3 minus H4 is Q dot. The last one is M dot B. H3 minus H4 is M dot A. H2 minus H1. Okay, so these are the energy balance equations here. So let's see, what do we know? We know the pressure of the steam. So P3 is 20 kilopascal and the quality. There is a quality X. When do we have a quality X of 95%? When we have saturated mixture. Then what is the quality X of saturated liquid? 0. What is the quality X of saturated vapor? 1. What is the quality X of compressed liquid? There is no quality X because compressed liquid is away from its saturation. What about super vapor? There's no quality X. By the way, the quality X is the ratio between saturated liquid and saturated vapor. When you have only saturated liquid, that is when quality X is 0. When you have 100% saturated vapor, then the quality X is going to be 1. If you have a quality X between 0 and 1, which is 0.95 quality X, that means we have saturated mixture. So we don't have to make another property diagram to determine the phase change process. Quality X3 is 0.95. This is phase change process number 3. And we know the mass flow rate, 20,000 kilogram per hour. Okay, we don't like hour, right? So m dot number 3, which is m dot of B, is 20,000 kilogram per hour. So you need to divide by 3,600 to get this number in kilogram per hour. It is to be cooled by water from a nearby river, which is this blue one. And we want to prevent thermal pollution. The river water is not allowed to experience a temperature rise above 10 degrees Celsius. What does it mean in mathematics? The temperature rise is 10 degrees Celsius. So what is the temperature rise? From T1 to T2. T1, T2. So the temperature rise, delta T, which is T2 minus T1 is 10 degrees Celsius. So this is our assumption. If the steam is to leave the condenser as a saturated liquid, so we have information at number 4. So still 20 kilopascal, P4 is 20 kilopascal, and it is phase change process number 2, saturated liquid. We want to determine the mass flow rate of the cooling water required. So what we want to determine is m dot of A. So this is what do we want? This is what we want. So among these 3 energy balance equations, which one do we use? It's pretty simple. Are we interested in the rate of heat transfer Q dot? No. So we're not going to use the first one. We are not going to use the second one. So we are going to use the third one. Since we are not interested in Q dot, why do we need to determine Q dot? Because if you use the first 2, you need to determine Q dot, right? So I'm going to use the third equation, this one. M dot B H3 minus H4 is M dot A H2 minus H1. So let's look at the left-hand side. Do we know M dot B? Yes, we have. Can we determine H3? Yes, because we know the pressure and the quality X. So when you have a quality X, it is saturated mixture. How do you determine H of saturated mixture? The linear interpolation equation. What is the linear interpolation equation? H3 is HF plus quality X times Hg minus HF. So that's how we determine H3. What about H4? That is the specific enthalpy of saturated liquid. When you have saturated liquid, how do you determine its property? Directly from the property table. So H of saturated liquid is going to be just HF. So H4 is going to be HF. And we already know m dot b. So left-hand side is okay. Let's look at the right-hand side. What is m dot a? Do we know? We do not know. This is what we want to determine. So this is the unknown. What about H2, H1? We only know the temperature change. But what is the system? River water. Even though it's water, do you expect a phase change of river water? We don't, right? If there's a phase change, we get free dinner. That you go to Island Park and sit down. In front of river, there's a cooked fish comes out, right? There is no phase change of river water, right? Yes, no, right? So as long as there is no phase change, that water can be considered as pure liquid. If you have a pure system, how do you determine its property? Specific heat. So how do you use specific heat? Do you remember? How do we use specific heat? U2 minus U1 is CVT2 minus T1. H2 minus H1 is CPT2 minus T1. This is only okay when you have a pure system, right? So what do we need to determine? H2 minus H1. How can we determine CPT2 minus T1? So H2 minus H1 is CP T2 minus T1. Then what is T2 minus T1? The maximum temperature rise is 10 degrees Celsius. So this one is 10 degrees Celsius. What is the specific heat of water? We can find it. Approximately 4.18 kilojoule per kilogram degree Celsius, right? So the right-hand side is done. Left-hand side is done. Can you determine m dot a? Yes, you can. So let's find H3. How do we determine HF? I know we need to find HF and HG. So, but where can we find them? From this pressure. If you know temperature, from that temperature. If you know pressure, from that pressure, right? So at 20 kilopascal, if you know pressure, what table you need to find? Saturated water, pressure table. Do we have it? Saturated water, pressure table. It's right here. Properties of saturated water, what table? Pressure table. And what is the pressure? 20 kilopascal. Oops, there is a 0.2. Is it 0.2 kilopascal? No, what is the unit? Bar. 1 bar is 100 kilopascal. 0.2 bar is 20 kilopascal. So this is the pressure of this steam. So what is HF? HF, this number. What is HG? This number. So this one. 251.4. What is the quality X? 0.95. What is HG? This one. 2609.7. What is HF? We just found 251.4. What about this HF? The same thing, 251.4. Then this one goes in here. When you calculate H3, goes in here. What is m dot b? Here. And what is H2 minus H1? Here. So how many unknowns? Just one. Can you find m dot a? Yes. 297.8 kilogram per second. Any question? That completes chapter 4. We have one more chapter to go. That's chapter 6, entropy. Yes. Oh, this one? These three? What do you mean? Oh, right. By the way, in your exam, you can have one formula sheet. You can write down any equation there, right? Of course, the governing equation should be provided. You cannot just say that, when this is the problem, in your exam, if you write this answer, course, you are not going to get full credit. You need to show how you calculate that. If you want to show how you calculate that, the first thing you need to show is, oh, not that one, but assumption. But after the assumption, you need to show what is the governing equation, right? Any exams, you need to write your solution clearly. Because if you didn't get the right answer, you can still get partial credit, right? But if I cannot understand your solution, how can I give you partial credit? The more you write, the more chance you can get partial credit, right? Any question? No? Okay. Entropy. This is the last chapter that we are going to review from Thermo 1. If we can finish in time, we can start Thermodynamics 2. We have 25 minutes. I think we have plenty of time. So there will be 3 items that we are going to study. 3 items, only 3. The first one is, are they really 3? 1, 2, okay, so there are 3 items that we are going to study. How do we evaluate this entropy, right? How can we find this entropy? When you have phase change material. And how can we find this entropy when you have a pure material? And what is entropy balance equation? So these are the 3 things, okay? Of course, the first one is very simple because evaluating an entropy value from a table is nothing different from, yes. Entropy is a thermodynamic property that shows how, how much waste energy is in your system. So for the same system, one can have, the higher useful energy, and then the other. Then the other system has higher entropy, even though the total energy is the same. Let's say, the simplest way to understand is that, what about if you have a 100 kilojoule of electricity? It's a very useful energy. Converting electricity to, the mechanical energy or thermal energy is pretty easy, right? So if you have if you have electricity, you can use a heater to, to produce, the heat, which means that converting electric energy into thermal energy. If you have a motor, like, the Tesla, you can convert electric energy to mechanical energy. So converting electric energy to another form of energy is pretty simple. In that case, the entropy of electric energy is pretty low. But once you convert, so now initially you had 100 kilojoule of electric energy. Now you converted everything into heat by using electric heater. So now you have 100 kilojoule of heat. Is it that useful as, the electricity? Not anymore. So even though if you only consider energy point of view, you still have the same energy, 100 joule of electricity, 100 joule of heat. However, this is less useful. So to show the difference between these 2 systems, we use a new thermodynamic, the property is called entropy. So our assumption is that, the entropy goes up when you produce unuseful energy, less useful energies. So the more heat you get, higher entropy you get, okay, for the same amount. So our assumption is that when you convert unuseful energy to unuseful energy, usually heat, because heat is, usually, practically the last form of energy. In other words, waste form of energy. So if you convert useful energy into heat, the system's entropy increased. So the one rule is, once entropy increased, you cannot decrease that entropy. Entropy only increase. So if you increase entropy, that process cannot be reversed. If you have electricity about this much, and then you convert it into a heat, then entropy increased. Then a process can only occur in the direction of entropy increase. So the other way is not possible. Like, that you already created heat. Now let's convert this heat into electricity. That is not possible because entropy has been increased. You get the idea? Yeah. Then how can we determine this entropy S? For phase change process, for phase change material, we use the same rule. We make a property diagram. You remember property diagrams such as TV diagram for given pressure, or TU diagram, TH diagram, right? In entropy, we use TS diagram for given pressure. What is this S? Entropy. And the graph looks like the same thing. T set SF SG. So you treat this entropy S the same as UVUH. That's how you determine entropy S when you have a phase change process, a phase change material. So that's number one. Then before we move on, before we go to the second part, which is finding entropy for pure system, let's solve a problem together in terms of entropy of phase change material. A well-insulated rigid tank contains 5 kilograms of saturated liquid vapor mixture of water at 150 kilopascal. Initially, 3/4 of the mass is in the liquid phase. So that means that you have a saturated mixture. And now we have an electric resistance heater placed in the tank, is now turned on, and until all the liquid in the tank is vaporized. That means initially it was a saturated mixture, and finally it is saturated vapor. Determine the entropy change of the steam during this process. We all know what is the change. It's going to be increase of entropy, because any process occurs in the direction of entropy increase. An ideal process is going to be when entropy remains constant. There is no process whose entropy goes down. That is impossible. Okay, so there are 3 processes. Like in general, entropy increase process, and one ideal case, entropy is constant. In other words, isentropic process. And impossible process is when entropy decreases. Then let's solve this problem. We have initially a saturated vapor, initially number 1, phase change process number 3, saturated vapor, and there was a energy transfer by this electric resistance heater. So there's an electric work enters the system, W in, until all the liquid in the tank is vaporized. So now at the final state, it is going to be phase change process number 4, saturated vapor. Okay. Then the question is, how can we determine the total entropy change? We can do that, no problem. First, let's to see what information do we have. First, we have the mass of the system. So the mass of the system is 5 kilograms. Okay, good. And now we know it is saturated liquid mixture, phase change process number 3. If you have a phase change process, if you have a saturated mixture, we need another thermodynamic property. What is it? Quality X, right? Do we know the quality X? Yes, 3/4 of the mass is in the liquid. What is the definition of the quality X? The ratio between liquid and vapor. When you only have liquid, 0. When you only have vapor, 1. So if 3/4 of the mass is in the liquid phase, that means only 1/4 is in the vapor phase. So what is the quality X? 0.25. If you want to use a mathematical form, you can say quality X is mass of vapor over mass of liquid plus mass of vapor. So what is the amount of the liquid? 3/4, 0.75. What is the amount of the vapor? 1/4, 0.25, 0.25. So you get 0.25, right? And pressure P1 is 150 kilopascal. And quality X is 0.25. So if you know pressure and quality X, can you analyze this initial state? Yes. If you want to find V, you can find it. If you want to find H, you can do it. If you want to find entropy S, you can do it. Then no problem in the first state. What about the final state? What do we know? Oh, that is saturated vapor. What else? That's all we know. So can you analyze the final state? Can you find H? Can you find U, V, S? You can't, because you only know it is phase change process number 4. So you need another information. So what is it? One thing you can see is it's a rigid tank. What does it mean when you have a rigid tank? Its volume is constant. Mass is constant. In other words, specific volume remains constant. So V1 is the same as V2. So if you know V2 and it is saturated vapor, then you can analyze number 2. Okay? So that's our plan. That means that we need to determine V1. How can you determine V1 when you have a saturated mixture? What is the equation you are going to use? Linear interpolation. So what is the linear interpolation equation? V1 is Vf plus quality X Vg minus Vf. Where can you find Vf, Vg? From either from pressure or temperature. What do we know? Pressure. So here is 150 kilopascal. So this is the pressure initially. And what is Vf? This one. What is Vg? This one. So I'm going to write it here. This is 1.0528 times 10 to minus 3. Remember, this number is after multiplying by 1,000 because actual Vf is very small. So you need to divide by 1,000. Quality X is 0.25. Vg is 1.159. Vf is again this number. So can you determine V1? Yes, we can. If you find V1, it is going to be, where is it? 0.29054. 0.29054 cubic meters per kilogram. Then this is the specific volume at the final state. So If you know specific volume, if you know, it is super vapor, you can analyze the final state. Okay, so I guess we are ready. Since we have all the necessary information at number 1 and number 2. So let's solve this problem. What do we want to determine? Determine the entropy change. How do you determine entropy change? You can calculate entropy change by final entropy minus initial entropy, right? When you hit a buffet, you will gain some weight. How are we going to measure your weight change? Your weight after leaving that buffet minus your weight before hitting a buffet, right? Same thing. If you want to determine the entropy change, you need to calculate the final entropy minus the initial entropy, right? There's no good restaurant in Mount Pleasant, so I usually go to, the dining hall. I like dining hall. Yeah, I like it. Is there more than one? I thought that there's only one. 3? I didn't know that. I didn't know that. No, I only went to the place, the next to this building. Dine and Connect. Right. That's where I go. Okay. So I only go to the best, right? You don't like that place? Oh, try other restaurants in town. Yeah, Dine and Connect is better. And they have a promotion for faculty. We got 50% discount. Once a week. Not every day, only Friday. And there's no tax. We are non-profit. There's no tip. So it's better than, the other places there, right? No? Now I got, your attention. Okay. So let's continue. I mean, seriously, if you go out there, is there any good restaurant in town? Name one. No. Never been there. Yeah, I always want to try, but they only open, in the dinner time, right? Yeah. Oh, okay. Any other places? What? Well, what is that? It's a fast food restaurant. No. What is? Yeah. I went there a couple of times. My friend has a membership there, so I usually get a discount. I only go there when my friends go there. When I want to go to a restaurant, I usually go to Chicago. Yeah, Chicago. Usually they have a good Korean restaurant, Vietnamese, Chinese. I like them. But the problem is that the 4-hour driving. What? Best place I know is called you can hit the Korean supermarkets there. They have a the restaurant inside. Usually the best rather than going into a sit-down restaurant. Of course. I mean, like for example, the biggest, the Korean glasses store chain is called H Mart. The one in Detroit is about a size of TJ Maxx. But if you go to Chicago, they have like 10 Korean supermarkets, each is bigger than Walmart. Yeah, that's crazy. Anyway, so now I got your attention. Let's continue. Yeah. Let's continue. I want to finish this chapter today so you can have new homework assignment. I know that I receive a lot of emails from you guys that when is the first homework due? I want to submit. Okay. Okay. So I think about 4 or 5 emails about the first homework due. Yeah, you guys are very motivated. I like that. Okay. All right. Okay, no more talking about buffet. Okay, I'm not going to talk about that. But now, if you want to calculate the change in entropy, you can calculate the final entropy minus the initial entropy. However, the final entropy and initial entropy, they are extensive properties. So if you want to use intensive properties, it's going to be total entropy change. It's going to be mass times the final entropy per unit mass minus the initial entropy per unit mass. So that's how you calculate that. What is the mass? M. We have that 5 kilograms. So this one is 5 kilograms. What about S1? We know it is saturated mixture, so we can use the same equation. Same equation. I'm going to copy this one, copy and paste. S1 is SF plus X1 SG minus SF. So where do we get SF SG? From this pressure table, there's a SF, this one, SG, this one. So let me write this one. 1.4336. Quality X is 0.25. SG is 7.2233. SF is 1.4336. So that's how you determine S1. S1 is 2.881. 2.881 kilojoule per kilogram Kelvin. So let me write it here. 2.881 kilojoule per kilogram Kelvin. What about the specific entropy at the final state? We can evaluate that because we know specific volume and it is saturated vapor. So where is saturated vapor on this table? We have this clue. This is the specific volume. Where is the specific volume? It is saturated vapor. So this specific volume is what? Not just V2, it is VG, right? It's a specific saturated vapor. So it is VG. Where is VG? Right here. So what do you need to find? This number. So 0.29 is greater than this one and less than this one. So the final state is between these two. Then its specific entropy is going to be also between these two numbers, right? So between these two. So how do you determine the exact specific entropy? By linear interpolation. How? We just said 30 minutes ago that was the last time in linear interpolation. So I'm not going to do that. So if you do the linear interpolation between these two numbers and these two numbers for this specific volume, you get the specific entropy for this specific volume. The answer is 6.729. 6.72943 kilojoule per kilogram Kelvin. So if you calculate the entropy change, it is 19.24 kilojoule per Kelvin. Any question? So what about if you calculate this value and it is a negative value? Is that right? Now, if you get 0, what does it mean? It's an isentropic process. So you didn't lose any entropy. So that process is reversible. Electric energy, mechanical energy, electric energy, reversible. Electric energy, heat, not reversible because entropy increased. Waste form of energy created. That's when entropy goes up. So any question about this one? Oh, right, this one, 19.24. No, S2 is 6.72943. S1 is this number. N is this number. So if you do the calculation, you get 19.24. So that's everything about how you evaluate entropy of a phase change process. Now the second part of this, yeah, so we don't have time. So we are going to talk about how to evaluate entropy change of pure system and how to solve entropy balance equation. So we only have 2 more sections and we can do them within 20 minutes. So from Tuesday next week, we can start Thermodynamics 2. Okay. Thank you.